Good morning. For lab this week, we are going to be looking at buoyant forces. So we've been talking about buoyant forces in class. Buoyant forces are the net effect of fluid pressure. And buoyant forces are around us all the time. We're constantly in an atmosphere of air, and the differences in air pressure between higher elevations and lower elevations creates a buoyant force itself. The buoyant effect is more noticeable in denser fluids like water. And so for this week's lab, what we're going to be doing is we're bringing out our metal samples. Here's brass, and here's aluminum, and here's lead. And we're going to measure their densities, but these densities are going to be measured differently from before. You know, we measured the densities of these back in week 1, I think, of the class. And when we measured the densities at that time, we were just measuring their mass and then measuring their different lengths and diameters and heights and using that to kind of directly determine density. In today's lab, we're going to use the density of different fluids and then we're going to submerge these samples in different fluids and measure the buoyant effect. So here's what the plan looks like. It's the buoyant force lab. Our objective for the day is to measure the density of some metal samples. Now along the way, what we're also going to get the density of is we have some propanol, specifically 2-propanol, that we're going to measure the density of this also. Now we are going to make some assumptions. I squeezed this in. I realized it wasn't on the board, but I found a place for it. It turns out that we're going to assume that the density of air is 1.20 kilograms per cubic meter, and that the density of water is 1,000 kilograms per cubic meter. So if you've noticed, I've got these 3 beakers here, and so what we can do is we can take each of the samples. So I could start with the brass sample, and I could drop it into the air and measure the buoyant effect, right? And then I can submerge it in the water and measure the buoyant effect there. And then, get it right off, I can submerge it in the propanol and measure the buoyant effect there. So that's the idea. So how much difference will I see in buoyant effect? Let me grab a paper towel very quickly. How much difference will we see in the buoyant effect? And what we've been talking about in class is that if the density of the fluid is higher, there's going to be more of a buoyant effect. Now the way we're going to be able to measure the buoyant effect is we're going to be using some balances. So here is our measuring device. Looks something like this. This is one of those kind of balances that you may have seen where you can actually adjust the weights. So the balances that we have, these have a string attached to them from below. So these balances, not only can you take something and set it on the platform on top to measure the mass, but you can actually hang objects. See if I can get this hook to go through here. Maybe I can't. I'll try it. I'm going to get this to work. Thank you for your patience. Well, okay, finally. So what we have a string attached with a loop, and there. So that string is attached to this platform from below. And that means that we can hang objects and we can measure, well, it's not really their mass when we have them in these fluids. What we're really, think of this, we're measuring the tension. And so what will happen is, if I drop this into a fluid, the tension will reduce. Now, the balance itself is not reading out newtons, it's actually reading out grams. And so let's see how we're going to deal with that possible confusion with units. So here's the diagram of what's going on. Here is the container full of air. Here is a container full of water. Here's a container full of propanol. And for each of these, the force diagrams look kind of similar. In each case, the force diagram consists of, there's a gravitational force based on the actual mass of the sample. So there's going to be an mg as a result. Now, there's also going to be a tension in the string. And up until now, we've kind of been ignoring the buoyant effect of air because it's small for most objects. So up until now, we've been saying that the tension is the same thing as the gravitational force in terms of numbers. As long as the object's not accelerating, T would equal mg. But now we're going to bring the buoyant effect in. And again, the buoyant effect for air is not going to be much of an effect. But the buoyant effect from the water and from the propanol, that's going to be significant. So for each of these force diagrams, in addition to the tension, we have listed the buoyant force. And for each of these three different materials, material 1, material 2, material 3. Now, the 1, 2, and 3 refer to the fluids, not the samples. The samples are not 1, 2, 3. The samples are brass, aluminum, and lead. The 1, 2, 3 here is fluid number 1, which is air, fluid number 2, which is water, and fluid number 3, which is propanol. And then we're going to take each of the samples and get a buoyant measurement. And the way we're going to get the buoyant measurement is we're going to say the buoyant force plus the tension combined, those two upward forces, are going to be equal to the gravitational force that's in the opposite direction. So that says B plus T is equal to mg, where m is the actual mass of these guys. Now, the buoyant force we've been talking about in class can be given by the density of the fluid times the volume of the fluid displaced. Now, in our lab today, these objects will always be fully submerged. So the volume of the fluid displaced will be equal to the volume of the objects. So that's something to keep in mind. And again, we've talked about this in class, but rho Vg, so that's the density of the fluid times the volume of the fluid, displaced times g. If we make that substitution in to this equation, we now have rho Vg plus mg equals mg. Now for material 1, which is air, fluid number 1, that would be the density of the air. M1 is what we're reading off the scale. So again, the scales ideally would be reading in force, tension 1, tension 2, and tension 3, but the scales here are listed in grams. So we'll think of the tension in terms of an effective mass times g. The tension is as if the mass was this much, or as if the mass were this much, or as if the mass were this much. Okay, so the M1s and the M2s and the M3s are the numbers that we're going to be reading off of the balance, and they're not the actual mass of the object. They're referenced to the tensions in each, that we'll measure in each of the three different fluids, 1, 2, and 3. So in fluid number 1, this is what the formula looks like. Now, I can cancel out the g's, so the gravitational field goes away. We've seen that before with these buoyancy problems. And we're left with density of fluid 1 times the volume being displaced plus the effective mass that the tension is measuring is equal to the actual mass. Okay, and then I can write that down for fluid number 2, and I can write it down for fluid number 3. So I'm going to get three formulas. Now I'm going to start off with just these two. I'm going to start off with the air and the water, and that's because the air and water densities we're going to say are well known. We're going to assume that the air we're working with, if it's at ocean level, you know, which we are at, the altitude here is pretty close to that. And roughly 20 degrees Celsius, then the density is going to be given by 1.20. So that's a pretty reliable number. And then water, I hope the water samples that we're using are 1,000 kilograms per cubic meter. So again, we're going to use densities of what we feel like are some pretty reliable densities for row 1 and row 2. Now I can play around with these formulas. What I could do is I could say, well, this equals little m and this equals little m. I can take this expression, the density v plus m, and set those equal to each other, and a couple lines of algebra solves for the volume. So what we're going to do along the way, I mean, we want to get the densities of these samples, but along the way, we can solve for the volume. We actually have a formula that we can write down what's the volume of this object. So that's kind of an interesting thing, right? You go, how do I measure the volume of this object? Well, I put it in a fluid, and I measure the tension on the string supporting it. So it's not like I put it in a beaker and then I look at the measurements on the beaker. Instead, I look at how much tension is required to support it. And, you know, the Buoyant force formulas that we've got say that should give us a pretty reliable volume for these samples. Now, what I could also do here is I could solve equation 1 for V. So here it is. V, according to equation 1, is m minus m1 over rho 1, where rho 1 is the density of fluid number 1, and m1 is the effective mass measured in fluid number 1. I can do that for fluid number 2, which is water. And then what I can do is I can solve this for m. So again, a few lines of algebra, and I've got this formula for the mass. So I'm going to say, yeah, you guys should be able to follow the algebra in this, okay? So these derivations are useful, and I think they're good practice for you guys. This is kind of like a homework problem or an example that we're looking at in lecture. So the mass I can get as m1 rho 2 minus m2 rho 1 divided by rho 2 minus rho 1. See, the formulas also look kind of pretty, so they have a nice symmetry to them. Now, what would happen in the case, let's imagine that the density of water is much, much larger than the density of air, which it is. So, you know, we keep saying that the density of water is like 800 times as large, over 800 times as large as the density of air. So that might suggest that, you know, what would be the mass of the sample if rho 1 is so small that we can just ignore it? So this formula says if I ignore rho 1 in the numerator and I ignore rho 1 in the denominator, then the rho 2's cancel out, and it says the actual mass of the object is basically the mass we measure when we set something on a scale. So that's our justification for why we have not been including buoyancy due to air during like the entire course up until now. So we can get away with it because the densities here are so low. All right, so we've got a formula that gives us the volume of the sample. That's pretty cool. We've got a formula that gives us a mass, but it's not going to be very different from M1. When I look at my data table, I'm going to have M1s and then some M2s and some M3s. I got 3 samples. So I'm going to have sample number 1, sample number 2, sample number 3. I'm going to get the volumes for them. I'm going to get the masses, but the masses here are going to be very similar to the masses I have in the column over here, because again, air is so much lower in density compared with these metals. And then what we can also do is we can get the density of the samples. That's what we said we're after. Density is given by m over v. I have a formula for v. I have a formula for m. I can take that formula, divide by that formula. The denominators cancel out. And so that says that the formula that I end up with, that's not right. Okay, I got to change this one. Oh, I'm glad I caught that. The denominators cancel out. I can see from the units there was already a problem here. Notice in terms of units, these are mass divided by mass per volume, so that's going to give me volume units. Here, the density units cancel out top and bottom, so the units are going to be in mass. Here, what's going to happen is, boy, I hope we did that right. Now I'm a little nervous. The rho 2 minus rho 1s, those canceled when we divided through. this should turn out to be M1 minus M2, and M1 is going to be bigger than M2 and M3, so that should be positive, and I think it's going to work. Okay, good thing we got that one fixed. And then finally what we can do is, remember we had a third equation that came from taking each one of the samples and putting them in the propanol. So we can take this third formula, there it is, the one we haven't used yet, and solve for the density of fluid 3. So we're treating the density of the propanol as an unknown, something that we want to go in and measure. So that's the propanol density formula. We can get that by taking in each row up here, we can take the M value. So let's say we did a bunch of measurements with the brass cube. So I'm going to take the brass cube, I'm going to get an M1, an M2, and an M3. I'm going to use this formula to get the volume of that brass cube. I'm going to use this formula to get a mass of that brass cube. And then I'm going to use this to get the density of the brass itself. And then finally I'm going to use this formula to get the propanol. So I can take the M here and the M3, this minus this, divided by this, and that will give me the density of the propanol. Okay? And then I'll step down to the next level here. I'll do the same thing for the aluminum. So let's say that we've got brass, aluminum, the board's filling up. I hope this is going to work. And then lead. So row number 1, let's say it's brass, row number 2 is aluminum, row number 3 is lead. And again, I'll just follow the same procedure. By the end of all my measurements and calculations, I will have 3 measurements of the propanol, and then I can report an average. That's the only column here where these 3 numbers should match. And so we'll take an average. None of these others, we're not expecting the others to match. So taking an average doesn't, it's really not meaningful. But this is a meaningful number for us. That's what's going to get reported as our overall measurement of the density of propanol for the day. So moving on to our results table. Now again, I didn't put units in. I mean, I know you guys should be able to put the units in yourselves, but I did. At first, I didn't put units in, but then I went back and I put some units in. So here's the results table: measured densities, accepted densities. Now, the accepted densities, again, you can look for these in your textbook. I'm guessing for the propanol, it probably isn't listed, and so, go online. You can easily look up. Now, it's specifically to propanol, so we should look that up. There's 1 propanol and 2 propanol, depends where the hydroxy group is attached. So we are I hope that's it. I hope I drew the right formula. So here's my tetrahedral carbon, and here's some methyl groups. Anyway, if that's not the right compound, let me know. Let's see. I think that's it. I think that's everything for the day. So again, there's some good formulas to play around with here. So I think we're ready to take a look at the setup and see what taking the measurements is actually going to look like. All right, if you guys have any questions, let me know. And we'll go ahead and take a look at taking the measurements. All right, so here's what the setup looks like for our buoyant force lab. Let's see what we have on the table here. We've got a balance setup. And there is a string attached to, if we look underneath here, the string is attached right onto the same device that holds this plate. And then we can measure the masses by adjusting the weights that are on here. Now, each time we do a measurement with this, we want to go back and re-zero. So if we look at the scale over here, there's a 0 mark. Maybe I'll grab the camera and bring it in for a closer look. But there's a counterweight here that I can rotate out or rotate in, and I can adjust that. Right now, it looks pretty good. I already went through and zeroed this, but I'll have to go back and double check the 0 for each one of the measurements. So I've got a string here, it's pretty thin, and then I have the fluid set up. So here is my beaker full of air, and here is a beaker with some water in it. Now, I want to have the metal samples completely submerged, and so I've been playing around with this. I think I've got this set up now. I did some preliminary measurements, and I think I got it set up so that for each of the metal samples, if I hang them from this string with the loop in it, that they'll be submerged. So that's the water. And then I have a smaller beaker with some extra water in case I need to pour a little water in or pour a little water out, depending on the size of the metal sample. And then I also have a beaker out here, a couple beakers, for the 2-propanol. So, and here is so I've got enough in here. Again, I was doing some preliminary checks with this. I think I have enough in this container that it will fill this, again, so that the metal samples will fit. They'll be submerged, but I'm not going to have propanol spilling out over the table. And then I put it back in the bottle and closed it because you could, it was vaporizing, and I wanted to preserve our propanol. And then I have a beaker with a little extra in here. Yeah, that's the propanol. But remember, it's not ethanol, so don't drink this. Make sure. All right. I think we're set to go. Here is the container of extra air. If we need to pour a little extra air in or remove some of the air, I have a small beaker of air right there. It worked out that, well, I tied the loop, and then I realized it was a little, I put a brick underneath here, so here's what the measurements are going to look like. So I'm going to grab one of these beakers. I know this is my beaker of air, and I'm going to grab, I'll start out with the brass sample, and so what I'm going to do is I'm going to hang this brass sample onto the string. Now I haven't got it submerged in the air yet, so I'll do that. I know, it's just for fun. So I'm going to put this in here, and then I'm going to settle this down. Now it was zeroed out before, but I can see that the balance has jumped. So placing something on this hanger does the same thing as if I had placed the brass sample on top of the plate on this balance. Okay, so 100, no, 200, no, 300, oh, 300 is too much. Come back to 200, and then, I don't know, 40, 50, 60, 70, 70 is getting pretty close, 80 is too much. And then I can, so this smaller scale measures right down to tenths of a gram. And again, I was playing around with the scale, and it pretty reliably, you can just zero in on individual tenths of a gram. You can see that. Well, let's show this. So I'm going to move this out. And you can see once I'm getting to 1 gram, it's getting pretty close. Let's see. So right now it overshot just a little bit. It's a little too much weight that I've placed here. So what I can do, it's a 271.5. I'm going to bring it back to 271.4. That definitely looks better. Now another thing I got to watch for here is with the balance, does it reliably return to the same point? I want to check for internal friction on the balance here. And it does look like it's returning. So it looks more like 271.3 maybe. 271.2. Okay. And that looks pretty well zeroed out. So I think I'm going to go with the 271.2 is what I'm at right now. Now, as long as we have the brass sample in place, let me write this down. 271.2 grams. As long as I have the brass sample here, maybe I'll do a complete set of measurements. So let me take the air away from here. I'm going to move the water in. Okay, I got to be careful here. I don't want to drop. This has happened in lab more than once, where myself or one of the students drop one of the samples onto the beaker and they break. So now I'm checking the brass and I can see it's entirely submerged. Now, earlier in the semester, we had done, I think the first week, we had done a density measurement where we talked about the hooks as kind of a problem. In fact, I think what I ended up doing on the data sheet for that lab is I took the hooks out and did all the measurements with the hooks out. Now, in this lab, we're facing a bit of a different situation because if it's completely submerged, including the hook, then what should happen is the results will be averaging over the density. So if I have this hook that is denser, if it's similar density to the material, it should have almost no effect if the density is similar. Now, I think the hooks, looking at them, I'm not sure. I mean, if this is an aluminum hook in a piece of aluminum, I think we're good. I'm not sure if it's aluminum or if it's steel. I should check and get a magnet out maybe and see if it's ferromagnetic. With the brass, if that's a steel hook, that's about the same density as brass, so it won't make too much difference. Lead is denser. Now the hook here looks different. It looks like maybe the hook itself is brass, but anyway, I'm leaving the hooks in, and that means that the densities we come up with will be averaged over that small contribution of the hook. And before we had measured the hooks, they were less than a gram, and so even for the aluminum sample, which is the lightest of all, that's only about a 1% of the mass of the sample. Okay, so, and the densities aren't zero, so the density issues that might come up are going to be, I'm going to say they're going to be really small. Anyway, I've got the brass inside here. Now this is with water, and so what we're guessing now is that the water is going to provide a larger buoyant force than the air did. And so what we're guessing here is the tension will be reduced. Now remember, these are really tensions. They're forces in our force diagram, but the scale here is calibrated in terms of grams. So this is the effective mass that we talked about in the presentation for the lab. So anyway, we're just reading these things off in effective grams. So let's see how much we have to back off. Let's see. I'm going to go back to 240. Well, 240 still seems like too much. Now, 230 is not enough. So let me go back and see what we're at here. 238 and a half, 239. 239 is coming in very close. Now again, I can go back and forth like 1/10 of a gram and see if there's a noticeable change. Right now it balances. If anything, I would back off maybe 1/10. That would put us at, let's see, 239.0 looks like a good measurement. Now I'm going to move it back 1/10 just to see if I can actually see a difference. And it's shifted up just a little bit. I'm going to back it off 1/10 more. Yeah, and now you can definitely see it's moving away. So again, I'm going to go with the 239.0. And I'm trying to get a good direct look. You know, if I look at an angle, when I look at those marks now at an angle, they don't line up. So it's a parallax effect. And so whenever we're reading something, I want to get in and look at it directly. And it looks like it's lined up right there. In fact, let me try an additional 1/10 of a gram. I think I like the 239. Yeah, don't make that mistake. Okay. So I've got 239.0. All right, now for the brass, we just have one more measurement and we're done with that sample. So there's not a lot of measurements being taken here, but the measurements we are taking, we want to check. Now I had talked about, I think the plan here was to zero everything, zero out the balance during the measurement. So I'm going to do that. I've got a sample here. I'm going to dry this off, let that dry a bit, and then I'm going to go back and check my zero. So has the balance somehow shifted? Am I still reliably getting zero when I zero out all of the weights? And it looks pretty good. So I might actually want to bring this out just a touch. So I'm going to adjust the counterweight just a bit. Okay, let me tip it and see if it comes back to equilibrium. That looks pretty good. Let me try it the other way. Ooh, let me just adjust the counterweight just a bit more. See what we end up with here. Yeah, I overdid it. Okay, so this is, now if this were, a more modern digital device, which we've got a lot of scales around the room, but there aren't any that we can measure masses from below. And these have continued to work well. So I think I've got this zeroed out now. So we're ready. Let's get out the propanol. Remember, this is propanol. It's got 3 carbons. It's not ethanol, which has 2. Oh, I don't know if it's going to fit. I don't think I had it measured right. Let's check and see. I think I need to pour a little bit of this out. All right, a little bit poured out. We can always add some if we decide we're a little short. Where is that sample? That sample feels pretty dry, so I got the water off of it. Here is the brass sample. Here it is going in. I've got it hooked on the loop. Don't break the beaker. The propanol did not spill out, so that's good. It's down inside. Now, let's see, is the propanol denser than water, or is the propanol less dense compared with water? If it's more dense, then the effective mass should go even lower. But if it's less dense, then we would expect that the effective mass is going to be a little higher. Now with water, this was 239.0 is the number that I have here. And so let me check the numbers here. So I'm going to put the 200 in. Let's see, 230. We should be able to go up to 230, 240. What about 250? So 250 is too much. So I am reading a higher mass from before. So it's 240, it's between 240 and 250 grams. And let me bring in this precision scale. I'll just put it in the middle. See what 245 looks like. It's going to be higher than 245. So let's go to 246. 246, we overshot. So it's somewhere between 245 and 246. So let's, again, I'm going to go to the halfway point here. Back off just a bit. That looks really good. So it looks really good at 245. 245.4. I'm going to tentatively write that down. Now, I do want to look 1/10 of a gram higher. And that moves away from, and then 1/10 of a gram lower. And that also moves away a bit. So I think that's the best, that's the most central value we have here. So I think that's it. So we've got the 3 measurements for the brass. The next thing to do would be to do the 3 measurements for the aluminum, and then also get the 3 measurements on the lead samples. And again, I'm handling the lead carefully, and I'm washing up in between all of these measurements. So anyway, that's what it looks like in terms of the measurements for the buoyant force. So we'll run the numbers and we'll see what we end up with. If you guys have any questions about this, here are the scissors. Here is the string. Anything else we need to point out here? That's the brick. This is our container of water. This is the container of propanol. We'll get this dried off and get these other samples ready to go on. So that's it. Stop by office hours if you've got any questions. We'll get those looked at.